At the end of this video, you should be able to discuss the dual wave particle nature of light and discuss the significance of the photoelectric effect in the line-emission spectrum of hydrogen to the development of the atomic model. Chapter 4, Section 1, the photoelectric effect. In the early 1900s, scientists conducted two experiments involving the interactions of light and matter that could not be explained by the wave theory of light. One experiment involved a phenomenon known as the photoelectric effect. The photoelectric effect refers to the emission of electrons from a metal when light shines on the metal, as illustrated in Figure 4-3 on page 93 of your text, or on the screen now. The mystery of the photoelectric effect involved the frequency of the light striking the metal. For a given metal, no electrons were emitted if the light's frequency was below a certain minimum, regardless of how long the light was shone. Light was known to be a form of energy, capable of knocking loose an electron from a metal. But the wave theory of light predicted that light of any frequency could supply enough energy to eject an electron. Scientists could not explain why the light had to be of a minimum frequency in order for the photoelectric effect to occur.
When light strikes a metal surface, electrons may be ejected. This process is called the photoelectric effect. Each metal has a characteristic energy level. If the incoming light is below this level, no electrons will be ejected. For example, this red light is not sufficiently energetic to eject electrons from cesium metal. Yellow light is also not energetic enough to eject electrons. Green light is energetic enough to eject electrons and current flows.
The particle description of light. The explanation of the photoelectric effect dates back to 1900, when German physicist Max Planck was studying the emission of light by hot objects. He proposed that a hot object does not emit electromagnetic energy continuously, as would be expected, as the energy emitted were in the form of waves. Instead, Planck suggested that the object emits energy in small specific amounts, called quanta. A quantum is the minimum quantity of energy that can be lost or gained by an atom. Planck proposed the following relationship between the quantum of energy and the frequency of radiation. E is equal to h nu. In this equation, E is the energy in joules of a quantum of radiation. Nu is the frequency of the radiation emitted, and h is a fundamental physical constant now known as Planck's constant. H is equal to 6.626 times 10 to the negative 34 joule seconds. In 1905, Albert Einstein expanded on Planck's theory by introducing the radical idea that electromagnetic radiation has a dual wave particle nature. While light exhibits many wave-like properties, it can also be thought of as a stream of particles. Each particle of light carries a quantum of energy. Einstein called these particles photons. A photon is a particle of electromagnetic radiation having zero mass and carrying a quantum of energy. The energy of a particular photon depends on the frequency of that radiation. So, the energy of a photon, E sub photon, is equal to h nu. Einstein explained the photoelectric effect by proposing that electromagnetic radiation is absorbed by matter only in whole numbers of photons. In order for an electron to be ejected from a metal surface, the electron must be struck by a single photon possessing at least the minimum energy required to knock the electron loose. According to the equation E sub photon is equal to h nu, this minimum energy corresponds to a minimum frequency. If a photon's frequency is below that minimum, then the electron remains bound to the metal surface. Electrons in different metals are bound more or less tightly, so different metals require different minimum frequencies to exhibit the photoelectric effect.
In 1900, Max Planck theorized that a hot object does not emit electromagnetic energy continuously. Instead, Planck suggested that objects actually emit energy in small, specific amounts, or quanta. Energy, he said, was quantized. In other words, the energy being emitted has only certain values, almost as though the energy is a packet. Some wavelengths of light carry only a little energy at a time. Others carry more. But the energy is always quantized. It is always in terms of the packet. The smallest possible amount, one packet or quantum, is defined as the minimum quantity of energy that can be gained or lost by an atom. Quantization becomes important when light or another form of energy interacts with an atom. Sometimes the incoming energy is enough to make something happen, other times it is not. Think of rolling a ball out of a pit. The energy must be enough to get the ball out of the pit all at once, or the ball will simply roll back to the bottom. Even if the energy of multiple rolls would add up to enough energy, the ball will not have been able to get out of the pit because the energy of each hit in itself was not sufficient. With enough energy in a single hit, the ball escapes from the pit. Similarly, if the packet of energy is not large enough, the atom is unaffected, despite the fact that the packets of energy keep coming. If the packet of energy is sufficiently large, however, the atom is affected. An electron, for instance, may become excited.
The energy of a photon is equal to the product of Planck's constant times the frequency of the photon. 93.7 megahertz is a common radio broadcast frequency. If we substitute 93.7 megahertz into the equation, we get the energy of the photon. This equation can be looked at differently by using the relation. The frequency of the photon is equal to the speed of light divided by the wavelength. This means that the energy of a photon is equal to Planck's constant times the speed of light divided by the wavelength of the photon. Blue light has a shorter wavelength than red light. From this relation, we can determine that blue light is more energetic than red light.
The hydrogen atom line emission spectrum. When current is passed through a gas at low pressure, the potential energy of some of the gas atoms increases. The lowest energy state of an atom is its ground state. A state in which an atom has a higher potential energy than it has in its ground state is an excited state. When an excited atom returns to its ground state, it gives off the energy it gained in the form of electromagnetic radiation. The production of colored light in neon signs, as is shown in figure 4-4 on page 94 of your text, is a familiar example of this process. When investigators passed electric current through a vacuum tube containing hydrogen gas at low pressure, they observed the emission of a characteristic pinkish glow. When a narrow beam of that emitted light was shined through a prism, it was separated into a series of specific frequencies and therefore specific wavelengths. Remember that lambda is equal to c divided by nu for that visible light. The bands of light were part of what is now known as hydrogen's line emission spectrum. The production of hydrogen's line emission spectrum is illustrated in figure 4-5 on page 95 of your text or on the screen now. Additional series of lines were discovered in the ultraviolet and infrared regions of hydrogen's line emission spectrum. The wavelengths of some of the spectral series are shown in figure 4-6 on page 95 of your text or on the screen now. They are known as the Lyman, Balmer, and Paschen series after their discoverers. Classical theory predicted that the hydrogen atoms would be excited by whatever amount of energy was added to them. Scientists had thus expected to observe the emission of a continuous range of frequencies of electromagnetic radiation, that is, a continuous spectrum. Why had the hydrogen atoms given off only specific frequencies of light? Attempts to explain this observation led to an entirely new theory of the atom called quantum theory. Whenever an excited hydrogen atom falls back from an excited state to its ground state, or to a lower energy excited state, it emits a photon of radiation. The energy of this photon, which is E sub photon, is equal to h nu. It is equal to the difference in energy between the atom's initial state and its final state, as illustrated in figure 4-7 on page 95 of your text or on the screen now. The fact that hydrogen atoms emit only specific frequencies of light indicate that the energy differences between the atom's energy states were fixed. This suggested that the electron of a hydrogen atom exists only in very specific energy states. In the late 19th century, a mathematical relationship that related the various wavelengths of hydrogen's line-emission spectrum was discovered. The challenge facing scientists was to provide a model of the hydrogen atom that accounted for this relationship.
Electrons in atoms can only have certain amounts of energy. Here we see several of the possible energy levels of a hydrogen atom. Suppose an excited atom of hydrogen has an electron at energy level 6. There is a probability that the electron will emit energy and jump back to a lower energy level. It could do so only by giving off energy equal to the energy difference between the two levels. If the electron makes a transition from energy level 6 to energy level 2, it emits the energy in the form of a photon of violet light. A transition from the 5th level to the 2nd yields a photon of blue light. From the 4th to the 2nd, a photon of blue-green light is emitted. A transition from level 3 to level 2 yields a photon of red light. Transitions that end in level 3 or higher produce infrared light. Transitions that end at level 1 produce ultraviolet light. The hydrogen spectrum is given by these 4 transitions to level 2. Out of the many wavelengths emitted, only those shown here are visible. The reverse process is also possible. If a bright white light is shown through a sample of unexcited hydrogen, photons can be captured by the electron in hydrogen if their energy corresponds to an allowed transition in the hydrogen atom. The result is an absorption spectrum. It has black lines that indicate that the gas has absorbed photons that have energies corresponding to the wavelengths of the bright lines of the emission spectrum of hydrogen. Each element has unique emission and absorption spectra. Here, the emission spectra of mercury and helium are shown with that of hydrogen for comparison.
At this point, you should be able to discuss the dual wave-particle nature of light and discuss the significance of the photoelectric effect and the line-emission spectrum of hydrogen to the development of the atomic model.